You carefully curate your cart. You click buy exactly once, and then your phone buzzes.
Right.
You look down, and your banking app is cheerfully informing you that you've just been charged twice.
Oh, that is the worst.
It's awful.
Yeah.
It's a massive breach of trust for you as the user. And, well, for the engineers behind the scenes, it's an absolute four-alarm fire.
Oh, definitely.
Because usually when we talk about software bugs in this deep dive, we're dealing with like a slow-loading page or maybe a weird CSS glitch.
Yeah, visual stuff.
Exactly. But the dreaded double charge involves real people, real money, and frankly, real panic. So today, we are going on a highly specific architectural mission to solve it.
And to do that, we're going to walk through this really fascinating architectural scenario that was recently outlined by Aaron Rose.
Yeah, the article is called The Secret Life of AWS, the Idempotency Key, Amazon DynamoDB, and it was originally published on tech-reader.blog.
Right, and the way he frames the problem is so unique. He introduces these two engineers, Margaret and Timothy.
I loved this setup.
It's great,
Yeah.
right, because rather than placing them in some sterile, fluorescent-lit Silicon Valley office, they actually work in this grand Victorian library in London.
It really sets a mood.
It does. It's a setting where code quality is treated with the exact same reverence as, like, ancient texts.
A real focus on craftsmanship.
Exactly. So we're going to step into that library with them and look at how they transform a decoupled, lightning-fast cloud system, which is, by the way, inherently prone to chaos, into an architecture that is mathematically safe and completely avoids duplicate data.
Okay, let's unpack this. Because right now, Timothy is staring at his logging dashboard, and the guy is pale.
Full panic mode.
He is looking at the exact nightmare we just described. The customer clicked buy once. The checkout service did its job perfectly and emitted a single solitary order-placed event.
Right.
But the downstream payment lambda function, the actual piece of code talking to the credit card processor, somehow executed twice.
And Timothy's initial reaction, which is pretty common, is to just assume his code is broken. He thinks he wrote a bug.
Sure, that's the instinct.
But Margaret pulls up a chair and explains that his code isn't actually the problem. The environment itself is the problem.
Right.
They are working in a modern distributed system, using an event bus to decouple their microservices. And when you rely on services like Amazon Event Bridge or SQS or SNS, you are relying on systems designed for extreme high availability.
Uncompromising availability.
Exactly. Their prime directive is to guarantee a message is never, ever lost, even if, say, a server rack loses power or some network cable gets severed somewhere.
But that extreme availability requires a pretty significant architectural trade-off. We are talking about the at least once delivery model.
Yes.
The system promises it will deliver your message at least one time, but to fulfill that promise, it basically has to accept that duplicates are inevitable.
Because if you think about the actual network mechanics happening under the hood, the event bus sends the order placed payload to the payment service. The payment service receives it, processes it, and then it's supposed to send an acknowledgement, like an ACK, back to the bus saying, hey, I got it. You can delete this message now.
But network partitions happen all the time.
All the time. So if there's even a momentary blip, that return ACK gets dropped.
Wow.
So the payment service successfully charged the card, but the event bus just never heard back.
So the event bus canics. It looks at its internal timer, realizes it hasn't received the ACK, and just assumes the payment service died before completing the job.
Exactly.
And to prevent data loss, it immediately fires a second identical copy of the order-placed event. It's a kind of like a highly dedicated mail carrier during a severe storm.
Oh, I like that.
Right. Like, imagine they drop off an envelope containing a crucial check on your porch. But as they walk back to the truck, the wind is howling, and they think, uh-oh, did that blow away?
Yeah, they can't be sure.
Because they cannot be 100% certain you secured that envelope, they literally print a duplicate check and drop it on your porch again. They would rather risk you cashing 2 checks than risk you not getting paid at all.
That is a perfect way to put it. That prioritization of delivery over cleanliness is the defining characteristic of cloud messaging. But this raises an important question.
Why do we put up with it?
Exactly. Why do developers tolerate this? Why not just use exactly once delivery systems and, avoid the duplicate mail carrier entirely?
Right.
Aaron Rose actually addresses this through Margaret's dialogue. Exactly once services do exist, things like SQS FIFO queues, but they introduce severe throughput limitation.
Because ensuring something happens exactly once requires global consensus.
Precisely the issue.
Right.
To guarantee a message is delivered exactly one time across a distributed cluster, the whole system basically has to constantly pause and check a global state.
That sounds slow.
It is. Every single time a message is routed, the nodes have to coordinate. They're like, did anyone else send this? Let me check the global ledger. Okay, cool. I'm clear to send.
Oh, wow.
Yeah, that constant locking and checking creates a massive bottleneck. So if your e-commerce platform needs to process tens of thousands of orders per second, that bottleneck will literally take your entire system down.
Right. It just can't keep up.
So for high-volume architectures, at least once is the required standard. You trade away a little bit of neatness to unlock massive horizontal scale and speed.
Which means the network is inevitably going to throw duplicate events at your application.
It's a guarantee.
You cannot rely on the infrastructure to protect you from double charges. The defense mechanism has to be built directly into your application logic itself. You have to design a system that expects duplicates and just neutralizes them.
And this brings us to the core concept of the deep dive idempotency. In a distributed context, making an operation idempotent means that no matter how many times the event bus hammers your service with the exact same event, the underlying state only changes once.
The outcome is always the same.
Right. Your application needs a memory. It needs a highly reliable way to look at an incoming payload and instantly recognize if it has seen it before.
So in the Victorian library scenario, Margaret opens the AWS console and she creates a dedicated Amazon DynamoDB table, and she calls it payment idempotency.
Yeah.
The whole strategy relies on an idempotency key, like a unique identifier, maybe an order ID or a UID generated by the front end that basically travels alongside the event payload.
Right, and the downstream payment function will use that key to track what it's already accomplished.
Okay, wait, let me stop you there and just look at this from the perspective of someone actually writing the code.
Sure.
If we just need to know whether we've seen an order ID before, why go through a complex architectural design? Why not just write a simple script?
What do you mean?
Like, imagine your Lambda function wakes up, receives the event with order ID 123, and it just queries the DynamoDB table, a really simple read operation. Hey, is order 123 in the table?
Okay.
If the database returns empty, your code writes order 123 into the table so you remember it for next time, and then reaches out to Stripe or whatever to charge the card. Just a straightforward read then write sequence. Simple, right? Why doesn't that solve our problem?
Well, what's fascinating here is that is the exact logical trap Timothy falls into.
Oh, really?
Yeah, and Margaret immediately points out that a simple read-then-write script introduces a catastrophic race condition.
Or a race condition.
Yeah, because we have to remember how cloud compute scales.
Mm-hmm.
We are not dealing with a single server processing one request after another in a neat little queue.
Right.
We are dealing with massive horizontal concurrency.
So multiple isolated environments running simultaneously.
Exactly. When the event bus retries that message, it might fire the duplicate within milliseconds of the original.
Oh, wow.
That means two entirely separate instances of your payment Lambda function spin up at the exact same time. Let's just call them function A and function B.
Okay, A and B.
Both receive the payload for order ID 123.
And because they are isolated micro VMs, they're completely blind to each other.
They have absolutely no idea the other exists. So function A executes step 1 of your script. It reads the DynamoDB table. Is order 123 here?
The database says no.
Right. But at that exact same microsecond, function B executes step 1. Is order 123 here?
Oh, no.
The database also tells function B no, because function A hasn't actually written anything yet.
It's a gap, the read-write gap.
The microsecond gap. Both independent functions receive a clear, positive signal to proceed.
That's bad.
So function A moves to step 2, writes the ID to the table, and charges the credit card. Function B simultaneously moves to step 2, overwrites the ID in the table, and charges the credit card a second time. Your safety mechanism completely collapsed because you assumed the database state wouldn't change in the microscopic fraction of a second between reading and writing.
It is genuinely terrifying when you realize that at cloud scale, you simply cannot trust what you read from a database if you plan to act on it a millisecond later.
You really can.
The truth just changes too fast.
Yeah.
So since a sequential read-then-write leaves that vulnerability window wide open, the architecture demands an operation that performs both the check and the write at the exact same time. It has to be completely indivisible.
Right. And in database engineering, that is known as an atomic operation.
Atomic?
It cannot be split into smaller steps.
Yeah.
It either fully succeeds as a single motion or it fully fails. And this is really Margaret's masterstroke in the story.
What does she do?
She goes into Timothy's Node.js payment service and completely deletes all that read-then-write logic, just trashes it. Instead, she adds a single DynamoDB put item command right at the very top of the function handler.
Okay, but here's where it gets really interesting. Because you can't just blindly put an item into the database, right?
Yeah.
That would just overwrite any existing record, and we'd be right back at square one with double charges.
Exactly.
So she utilizes a condition expression. Specifically, she attaches the attribute no Texas condition directly to the put item command.
Yes. By appending attribute no Texas engine, Margaret is leveraging DynamoDB conditional writes.
Okay.
She is sending a highly specific instruction to that database engine. She's saying, insert this order ID, but only if this exact partition key does not currently exist.
Ah.
The critical shift here is that the conditional logic is no longer happening in Timothy's application code. The responsibility is pushed all the way down to the DynamoDB storage node itself.
So how does pushing it down to the database engine actually solve the concurrency issue?
Because the database engine has the authority to issue a lock.
Oh, a lock.
Yeah. When those two identical requests from function A and function B hit the DynamoDB cluster at the same microsecond, they are targeting the exact same partition key. The storage node processing that partition acts as the ultimate referee. It serializes the request. It grants an atomic lock to function A, evaluates the condition, sees the ID doesn't exist, and writes the data.
And what about B?
While that single motion occurs, function B is locked out. By the time function B's request is finally evaluated a microsecond later, the state has changed.
The lock closes the vulnerability gap entirely.
Exactly.
So function A succeeds, it writes the idempotency key and moves on to charge the credit card. But wait, what happens to function B?
Yeah.
Because the event bus sent a duplicate, Lambda spun up an environment, and now DynamoDB has actively rejected its right attempt. Doesn't the whole system just crash?
See, this is where defensive engineering becomes truly elegant. When DynamoDB rejects that second write because the condition failed, it doesn't just quietly drop the request.
Okay.
It throws a highly specific error back to the Lambda function. It's called a conditional check failed exception.
It essentially sends a flare-up to the application saying, hey, I stopped you because someone else already did this.
That is exactly the purpose of the exception. Because the error is so predictable and so specific, Timothy can just wrap his put item command in a try-catch block designed to trap that exact exception.
Oh, brilliant.
When function B catches the conditional check failed exception, it experiences this moment of self-awareness. It instantly realizes, I failed to write the idempotency key, therefore I must be the duplicate event.
It recognizes its own nature.
Yes.
And once it knows it's the second copy, it safely aborts the checkout flow and never even reaches out to the payment gateway.
Right.
The customer's credit card is safe.
Right.
But wait, if function B catches an error and halts its execution, doesn't that create a new problem with the event bus?
How so?
Well, if EventBridge sent the message and the Lambda function essentially errored out, EventBridge is going to assume the message failed to process right. It's going to wait for its internal timer and then send a third copy and a fourth copy, endlessly retrying.
You nailed it.
Yeah.
And that is the final crucial piece of the mechanism. You have to manage the relationship with the event bus. When Timothy's code catches that conditional check failed exception, it purposefully swallows the error.
Swallows it.
It refuses to pass the panic back up the chain. Instead of failing, the catch block forces the Lambda function to return a success HTTP 200 response back to EventBridge.
Wow. It lies to the event bus.
It's a totally benevolent lie.
That's hilarious.
It tells EventBridge, yes, I received this order payload and I handled it perfectly. You can delete this message from your queue.
Oh, that's so smart.
By returning success, the bus receives its ACK, crosses the event off its list, and stops the retry cycle. The duplicate is fully neutralized, the downstream microservices remain completely unaware of the hiccup, and the system continues running at maximum speed.
It is a beautifully complete, mathematically safe defense mechanism.
It really is.
But, solving one massive architectural problem almost always introduces a new infrastructure friction point. Timothy actually immediately spots the long-term flaw in their new design. If the system is saving every single order ID into a DynamoDB table just to check for duplicates, that table is going to experience infinite storage bloat.
It's a highly relevant concern for real-world scaling. I mean,
Yeah.
if you are running a major e-commerce platform processing millions of transactions a month, that idempotency table will quickly balloon into billions of rows.
Timothy asks Margaret if this massive table is going to cost a fortune to maintain. And honestly, if we were dealing with traditional databases, the answer would be yes.
Oh, for sure.
You would have to write these complex background cron jobs to periodically scan the database and delete records that are older than a few days.
And running those massive delete scripts introduces severe complications regarding cloud economics, particularly with DynamoDB's pricing model.
Right, because of how they charge you.
Exactly. You pay for storage, obviously, but you also pay for write capacity units, or WCUs.
The WCUs, yeah.
Deleting an item is actually considered a write operation. It requires actual compute power.
To put that in perspective for you, imagine your database is a high-end restaurant kitchen.
Okay.
Your most expensive, valuable resource is your head chef. That's your write capacity.
I like this.
If you write a background script to delete millions of old idempotency keys, it's like forcing your head chef to stop cooking meals for paying customers so they can go wash dishes and take out the trash.
Wow.
You are burning expensive compute resources on basic housekeeping, which drives up your AWS bill and potentially throttles the performance of your live application traffic.
That is a phenomenal way to visualize the friction of manual deletion.
Yeah.
You never, ever want your primary compute handling garbage collection.
Right.
Margaret knows this, which is why she introduces Timothy to time to live, or TTL.
So she doesn't write a delete script at all.
She doesn't have to.
Yeah.
The application doesn't need to remember every order until the end of time.
Because the danger passes.
Exactly. The danger of a duplicate event from a service like EventBridge or SQS usually passes within milliseconds. Even in a catastrophic outage scenario with, extended retries, the threat is entirely gone after a few days.
Makes sense.
So Margaret configures the DynamoDB table with a TTL set to 30 days. When Timothy's code initially writes the idempotency key, it just appends a simple timestamp indicating when that record should expire.
So how does TTL actually solve the head chef problem?
If we connect this to the bigger picture, TTL operates entirely behind the scenes at the storage node level. DynamoDB just runs these background processes that constantly scan for expired timestamps.
Okay.
And when it finds them, it simply drops the data. And the absolute brilliance of this mechanism is that DynamoDB does not charge you write capacity units for TTL deletions.
Oh, wow. It's like having an invisible background sanitation crew that clears the tables and washes the dishes without ever stepping foot in the kitchen or bothering the head chef.
It happens essentially for free.
That's incredible.
By utilizing TTL, the idempotency table stays lean. You aren't digging through 5 years of dead transactional data to verify a fresh idempotency key, so your read latency stays incredibly low.
Right.
Your storage costs remain near zero, and your provision compute is completely reserved for handling actual customer orders.
So if you look at the whiteboard in that Victorian library, Timothy came into the session with a decoupled, high-speed cloud architecture that was occasionally charging customers twice because he trusted the network.
Which you can never do.
Never. And by the end of the session, he has an architecture that is still highly decoupled and incredibly fast, but it is now mathematically resilient to the realities of distributed systems.
It represents a fundamental evolution, really. It's moving from writing code that assumes perfect conditions to defensive engineering that expects and gracefully handles failure.
So what does this all mean for you, the listener, navigating these complex environments?
Yeah, let's bring it together.
If we zoom out and distill the journey we've taken today based on Aaron Rose's scenario, the core takeaway is a necessary shift in mindset. Event-driven architectures prioritize message delivery above all else.
Absolutely.
Duplicates are not an error you can fix. They are a fundamental feature of high availability. Because you cannot stop the network from sending duplicates, you must embrace idempotency at the application layer.
You have to.
You isolate state changes by requiring unique idempotency keys. You completely avoid the race condition vulnerability by pushing atomic locks down to the database engine using DynamoDB conditional writes.
Right.
You elegantly handle the inevitable failure state by catching the exact exception and feeding a benevolent success signal back to the event bus.
The benevolent lie.
The benevolent lie. And finally, you keep the entire defense mechanism economically viable by leveraging time to live for background garbage collection.
It is a masterclass in building trust into trustless environments. But, as we wrap up, I want to leave you with a concept that pulls this architectural pattern out of the server room and into your daily life.
Oh, okay.
We've spent this time analyzing idempotency as a strict database mechanism to protect computer systems. But what happens when we apply this exact same mindset to human processes?
Human idempotency. That is an incredible angle.
Think about the workflows across your organization. Think about your email inbox, right? Or a shared customer support queue, or how your team delegates urgent tasks in Slack. How many times have you and a colleague accidentally replied to the exact same client or duplicated hours of research simply because you didn't know the other person was already working on it?
You are describing a literal human race condition. Two independent workers receiving the same urgent payload, checking the current state, seeing no one has claimed it, and simultaneously executing the task.
Exactly. Our human workflows are overwhelmingly built with at least once delivery in mind.
It's so true.
A manager fires the same request at multiple people to guarantee it gets done, prioritizing completion over efficiency, which inevitably leads to massive duplication of effort and burnout. How much chaos, friction, and wasted time could we eliminate if we designed our own personal idempotency keys?
What would a human conditional write even look like?
It means establishing clear atomic signals the exact moment a task is touched. It means creating workflows where claiming a task and beginning a task are an indivisible, visible motion, preventing anyone else from wasting their time on a duplicate effort.
I love that.
It is about building systems, whether in code or in human communication, that gracefully handle the chaos of multiple inputs.
Designing our human processes to be idempotent. I love that provocation. It takes the deep technical wisdom of that Victorian library and applies it to our own messy, decoupled human lives.
Exactly.
Well, thank you for joining us for this deep dive. We hope you feel significantly more equipped to navigate the realities of distributed systems, race conditions, and cloud economics. Take these concepts, build mathematically safe architectures, and keep exploring the secret life of the systems running our world. We will catch you next time.